Somewhere in the constellation Aquila, roughly 12,000 light-years from where you are sitting right now, a star did something that had never been directly witnessed in the entire history of astronomy. Over the course of about 10 days in the spring of 2020, it brightened by more than 100 times its normal output, then stayed strangely warm in infrared light for months afterward, glowing low and cool instead of hot, which is backwards from almost everything else that makes a star suddenly flare. It took astronomers 3 years of careful analysis to work out what they had actually caught on camera. What they found was a planet, a gas giant not far off the mass of Jupiter, spiraling into the body of its own star and disappearing inside it. This is why that faint, almost missed pulse of light sitting in an old telescope archive matters so much. It is the first time our species has ever caught a world dying while the death was still happening, instead of only ever finding the wreckage afterward. Tonight we are not going to spend our time on the worlds we hope are alive somewhere out there. We are going to spend it on the worlds we can already prove are gone. Swallowed, shredded, frozen out, stripped bare, thrown loose into the dark with no star left to call their own. And what all of that, taken together, quietly tells us about the actual shape of the universe we live in. Most conversations about life beyond Earth get stuck between two extremes. Either the galaxy is quietly full of neighbors we simply have not met yet, or it is essentially empty, and we are some kind of cosmic accident sitting alone in the dark. Neither picture actually matches what the last 15 years of direct observation have turned up. What the evidence increasingly points toward is something closer to a universe that behaves like a construction site and a demolition site running at the same time, almost everywhere, almost constantly. And we only ever catch small, scattered glimpses of either process because both are happening far outside the narrow slice of sky and time we happen to be watching at any given moment. Worlds are being built. Worlds are being taken apart. Some of that taking apart, it turns out, we can now watch happen in something close to real time. The mechanisms behind all of this are not exotic in the sense of requiring strange new physics. Every single one of them, gravity pulling too hard, radiation stripping away gas, a collision between two large bodies, a star finally running out of room for the planet orbiting it, is built from the same handful of physical principles taught in an ordinary introductory astronomy course. What has changed is not the physics. What has changed is the instruments, patient enough now, sensitive enough now, watching long enough now, to actually catch these ordinary physical principles playing out on individual, named worlds rather than only ever being inferred from statistics and educated guesswork. That shift, from theory to direct observation, is genuinely recent, and it is the reason a conversation like this one could not have been had with this much specific, confirmed evidence even a single generation ago. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. Start with the easiest kind of dead world to picture, because it is not really dead in the sense of having been killed. It simply never got to keep its home. Astronomers call these rogue planets, sometimes free-floating planets, and the name says almost everything. A rogue planet is a world with planetary mass, planetary composition, sometimes even planetary weather, that is not in orbit around anything. No star warms it. No star lights it. It drifts through the space between star systems in permanent, total darkness, following whatever path it was given the moment it either formed on its own from a collapsing cloud of gas, too small to ignite into a star, or was thrown out of a young planetary system by the gravity of its own siblings, before that system had time to settle down. For a long time, this was mostly theory. Planet formation is a violent, crowded process. Young systems are stuffed with more planets and planetary embryos than their final, mature version usually keeps. As bigger bodies grow and their orbits begin to cross, something has to give. Some worlds get swallowed by the star. Some get flung into wide, frozen orbits at the edge of their system. And a significant number get thrown out entirely, accelerated past the speed needed to ever come back, sent out into interstellar space forever. Simulations of young systems suggest that being ejected this way is not a rare accident. In many models, ejecting at least one planet is closer to the ordinary outcome of a system settling down than the odd exception. Not every rogue world necessarily starts out orbiting anything at all. A separate formation path exists for at least some of the smallest, coldest clumps of collapsing gas in a star-forming nebula. Clouds of material too small and too cool to ever ignite nuclear fusion and become an actual star, but still capable of condensing under their own gravity into something with planetary mass, drifting freely from the very beginning, never attached to a parent star in the first place. Telling these two populations apart from a distance, an object that formed alone from the start versus an object that formed around a star and was later thrown out, is extremely difficult, since both end up looking essentially identical once they are drifting through interstellar space with no light of their own. Some of the objects the James Webb Space Telescope found, scattered through the Orion Nebula, likely belong to each category, mixed together in the same survey, indistinguishable without far more detailed follow-up study than a single imaging campaign can provide. Then, in the closing months of 2023, the James Webb Space Telescope gave that theory a very concrete, very strange piece of evidence. Surveying a small patch of the Orion Nebula, a stellar nursery about 1,350 light-years from here, astronomers found more than 500 free-floating objects with planetary mass drifting among the newborn stars, unattached to any of them. That alone would have been a significant discovery. What made it strange was a smaller detail buried inside it. Roughly 9% of those free-floating worlds were not alone. They were paired up, two planetary mass bodies orbiting each other, separated by distances tens to hundreds of times the space between Earth and the Sun, with no star anywhere nearby to have organized them that way. Astronomers nicknamed them Jupiter Mass Binary Objects, or jumbos for short, and masses in the pairs ranged from roughly 6/10 of Jupiter's mass up to about 14 times it. Nobody currently has a clean explanation for how a pair like that forms. Planets are supposed to form around a star, in a flattened disk of gas and dust, orbiting a single central point of gravity. A pair of planets orbiting each other with no star in sight breaks that picture. Some researchers think they may be failed attempts at binary star formation. Clumps of gas that almost became two small stars but ran out of material before nuclear fusion ever ignited. Others think they were once a pair of planets around a young binary star system, kicked out together during a close gravitational encounter, still bound to each other even after their shared home star system let them go. Either way, the jumbos are not a handful of oddities. They are a measurable fraction of an entire nursery full of drifting worlds that were never going to belong to anyone. The harder number to sit with is how many rogue planets like this might exist across the whole galaxy, not just in one nebula full of newborn stars. Because free-floating planets do not shine, and they do not reflect much light either, they cannot be found the way ordinary planets are found, by watching them cross in front of a star. Instead, almost everything we know about their numbers comes from a technique called gravitational microlensing. When a rogue planet happens to pass almost exactly between Earth and a much more distant background star, its gravity briefly bends and magnifies that star's light. For a few minutes to a few hours, the background star appears to flare, then fades back to normal, as the rogue planet moves on. The event never repeats. It cannot be pointed at again. Whatever mass and distance can be worked out has to come from that single brief flicker. A survey using this method, run for 9 years from an observatory in New Zealand, produced one of the more startling estimates in modern planetary astronomy. Based on the frequency of these brief flickering events, the team concluded that free, floating, roughly Earth-mass planets could outnumber the stars of the Milky Way, possibly by a wide margin. Estimates built on that survey have ranged from something like 1 rogue planet for every star in the galaxy, on the conservative end, up toward 20 for every star, which would put the total figure for our galaxy alone somewhere in the trillions. Other independent surveys have landed on lower numbers for the biggest, Jupiter-sized rogues, while still finding growing evidence for enormous populations of smaller ones. Getting a genuinely confident mass and distance out of a single microlensing flicker, rather than just a rough statistical guess, requires an additional trick beyond simply watching the light curve rise and fall from one location on Earth. Because Earth itself is moving through space, and because the geometry of the light-bending event depends on the precise relative motion between Earth, the rogue planet, and the distant background star, observing the same event simultaneously from 2 very different vantage points, one from the ground and one from a spacecraft stationed millions of kilometers away, allows astronomers to measure a subtle shift in the timing and shape of the light curve between the 2 viewpoints. That shift, called the microlensing parallax, breaks the usual ambiguity between a small nearby object and a larger, more distant one, both of which can otherwise produce nearly identical light curves from a single vantage point alone. Only a small number of rogue planet candidates have ever been measured this way, with both a confident mass and a confident distance attached, precisely because it requires 2 working observatories, one in space, watching the same few minutes of sky at the same time, purely by chance. On the one specific night, a given rogue planet happens to drift across the right patch of background stars. The honest state of the science is that we have confirmed only a small handful of individual rogue worlds through direct detection. One, spotted through the OGLE survey, produced a lensing flicker lasting barely 40 minutes and was estimated at only about a third of Earth's mass, among the smallest free-floating objects ever measured this way. Another, announced by the Korea Microlensing Telescope Network survey in early 2025, was unusual because astronomers managed to pin down both its mass and its distance at once, using simultaneous observations from ground-based telescopes and a space telescope working together. That planet came out to roughly 70 times Earth's mass, closer to Saturn's size, drifting about 10,000 light-years from here. Likely a world that formed around a star and was later cast loose rather than one that condensed on its own in open space. What is any of this actually like? If you could stand on one, a rogue planet the size of Earth, ejected from its birth system, carries no sun in its sky, ever. There is no day. There is no sunrise. There is only the background starlight of the galaxy itself, faint and cold and useless for warmth. And yet some planetary scientists have pointed out that total darkness does not necessarily mean total deadness. A rocky world large enough to hold onto a thick blanket of hydrogen in its atmosphere, or one still cooling from the leftover heat of its own formation and the slow decay of radioactive elements in its core, could in principle keep a liquid ocean running deep beneath a frozen crust for billions of years, entirely without starlight, heated from the inside rather than from above. Nobody has found direct evidence that any rogue planet actually does this. It remains a hypothesis built from physics that is otherwise well understood. But it means a rogue world is not automatically a dead world in every sense of the word. It may simply be a dead world of a very specific, very quiet kind, warmed only by its own leftover fire, wandering a galaxy full of stars it will never again belong to. There is a related population worth mentioning here too. Smaller objects that pass through a solar system rather than forming inside one and getting thrown out of it. Twice now, astronomers have confirmed an object entering our own solar system on a trajectory so fast and so unbound that it could only have come from interstellar space. One shaped like an elongated, tumbling sliver of rock, the other clearly a comet, both of them simply passing through, never to return, on their way to some other part of the galaxy entirely. Neither of those two visitors was a rogue planet in the full sense. They were far smaller, closer to asteroid or comet scale. But their existence, confirmed with certainty rather than inferred statistically, is a small, direct reminder that interstellar space is not actually empty of solid material drifting between the stars. It is full of debris of every size, from dust grains up through boulders up through, if the rogue planet surveys are anywhere close to correct, entire worlds. What a survey like the upcoming Nancy Grace Roman Space Telescope is expected to change is not the existence of these worlds, which is already about as well established as an indirect detection can be, but the precision of the count. Roman is designed to stare continuously at dense fields of background stars toward the crowded center of the galaxy for extended stretches of time, exactly the kind of patient, wide field, watching that microlensing needs to catch enough brief flickers to build a real statistical picture instead of a small handful of individually confirmed cases. Researchers involved in planning the mission have suggested it could detect free-floating Earth mass planets in numbers many times larger than every previous survey combined. If that holds up, the current uncertainty, somewhere between roughly one rogue world per star and something like 20 per star, should finally start collapsing toward a single, confident number. Until then, the honest answer is that we know these worlds exist in serious numbers, and we do not yet know precisely how serious. Picture standing on the frozen surface of one of these worlds anyway, just for a moment. There is no sunrise, because there is no sun close enough to matter. The sky above is simply the ordinary night sky of the galaxy. The same scattering of far-off stars you could see from Earth on a clear night, except it never changes, never brightens, never sets, because there is no orbit around a nearby star left to turn day into night and back again. If the planet still has enough of an atmosphere to hold on to, that atmosphere itself may have frozen solid long ago, fallen out of the sky as a thin crust of frost on top of the rock and ice below, because there is no starlight left to keep any gas warm enough to stay a gas. Whatever heat exists on a world like this comes entirely from underneath, from the planet's own leftover formation, warmth, and the slow radioactive decay ticking away in its core. The same heat sources that still gently warm the inside of our own planet today, except with absolutely nothing arriving from outside to add to it. It is, if the hypothesis about deep liquid water holds up on even a fraction of these worlds, possibly one of the strangest kinds of habitat physics currently allows for. Life, if it exists there at all, would have evolved in a permanent bottle, sealed off from starlight for its entire history, never once seeing the thing every living thing on Earth has always taken for granted. It is worth understanding just how violently a planet has to be treated in order to end up in this condition in the first place. Escaping a star's gravity entirely, rather than simply being nudged into a wider orbit, requires a very specific and very large kick. A planet has to be accelerated past what astronomers call the local escape velocity, the speed above which an object is no longer gravitationally bound and will keep drifting outward forever, rather than eventually curving back. For a planet, sitting roughly where Earth sits, relative to our own sun. That threshold speed is measured in tens of kilometers per second, considerably faster than almost anything in a young, settling planetary system would normally be moving on its own. The only realistic way to reach that speed is a close, violent gravitational encounter with another large body, a near-collision course with a neighboring planet or a passing star that flings the smaller object outward, the way a slingshot flings a stone, converting a close, dangerous pass into raw outward momentum in a matter of hours or days. A useful comparison sits right at the edge of our own solar system's recent history. When the first confirmed interstellar visitor was tracked, passing through our own neighborhood, its measured speed relative to the Sun was fast enough that it could never have originated here, and fast enough that it could never be captured into a bound orbit around our star, no matter how it approached. That same category of speed, once achieved by an ejected planet during its own violent departure from its birth system, becomes permanent. There is no slowing back down afterward. Once a rogue world is moving fast enough to leave, it simply keeps going, for as long as the universe continues to exist, unless another star system happens to catch it by pure chance, many thousands or millions of years later. Rogue planets tell us something about worlds that got cast out. The next kind of dead world tells us something almost the opposite. These are worlds that never left. They got pulled in instead, closer and closer, until the star that made them also ended them. Return to that strange brightening event in Aquila, when the Zwicky Transient Facility, a wide-field survey camera in Southern California that scans the entire visible sky every few nights, first flagged the outburst in the spring of 2020. The initial guess among astronomers was ordinary enough. Sudden brightenings like this are usually one of two things: a nova, where a dying star's surface briefly detonates, or two stars merging into one. Both produce a fast, hot flash of light. What made this event strange was that it did not behave like either. The optical brightening faded within about 10 days, far too quickly and far too faintly for a stellar merger, releasing something like 1,000 times less energy than any known merger of two full stars. And instead of cooling and fading in every wavelength the way a spent flash should, it stayed unusually bright in the infrared for around 100 days afterward, a signature of cool material, not hot material. Cool and bright do not normally go together. Something about this event was producing light, the wrong temperature for its brightness. The explanation the research team eventually settled on, published in the journal Nature in the spring of 2023, was that they had watched a sun-like star, roughly 10 billion years old, in the slow, ordinary process of expanding as it ages, finally reach down and swallow a planet that had been orbiting so close it could no longer resist the pull. The planet was probably a gas giant, not much more than 10 times the mass of Jupiter, quite possibly closer to Jupiter's own mass, orbiting on a timescale of only a handful of days. As the aging star's outer layers swelled outward over hundreds of thousands of years, the planet found itself skimming closer and closer to the stellar surface, until friction and gravity together took over, and the planet spiraled in during what was likely just the final stretch of a much longer, much slower decline. When it finally plunged into the star's outer layers, the star itself briefly puffed up to something like 4 times its normal size and brightened correspondingly, before settling back down to roughly what it had looked like before, as though nothing unusual had happened at all. One of the astronomers on the Discovery team put it about as plainly as this kind of moment deserves. It was almost as if the star ate the planet and forgot. What makes this discovery matter beyond its own strangeness is that astronomers had already predicted, for decades, based purely on stellar physics and on the leftover chemical fingerprints found in some aging stars, that this kind of engulfment must be happening somewhere in the galaxy on a regular basis. Nobody had ever caught the moment itself, only the before and the after. Now, there was a middle, and it turns out we do not have to look 12,000 light-years away, or wait for a decades-old survey to notice something strange in an archive, to watch a planet mid-execution. There is one doing it right now, close enough and bright enough that it has been studied in detail since the year it was found. It is called WASP 12b, and it sits about 1,300 light-years away in the constellation Auriga, orbiting its star in barely more than a single day. WASP 12b is what astronomers call an ultra-hot Jupiter, a gas giant so close to its star that its permanent daylight side sits at a temperature above 2,000 degrees Celsius, hot enough to vaporize most rock and keep clouds of metal in its skies. It orbits so tightly, at a distance only a small handful of times greater than the separation between Earth and our own moon, that the star's gravity has physically stretched the planet out of a sphere and into something closer to an egg shape, distorted along the line pointing toward the star, the same way our own moon raises tides in Earth's oceans, only far more violently, because the pull here is enormous. Since WASP 12b was discovered in 2008, astronomers have been timing the exact moment it crosses in front of its star, transit after transit, year after year. Those timings have not stayed steady. The interval between each crossing has been shrinking by a small fraction of a second every year, but consistently, in a single direction, for well over a decade of observation now. That shrinking interval is the signature of an orbit that is actually decaying, not just wobbling. The planet is spiraling inward, the same way ZTF's swallowed planet almost certainly did in its own final stretch. And researchers who have modeled the decay rate put the remaining time before WASP 12b is fully consumed by its star at somewhere around 3 million years, a blink of an eye by the standards of a system that is already billions of years old. Its atmosphere is already bleeding away under the heat and radiation, streaming off into a faint trailing cloud of gas around the star, carrying with it detectable amounts of exotic molecules cooked up under conditions no rocky world could survive. WASP 12b is not a hypothetical. It is not a projection from a model with wide error bars. It is a planet with a measured, shrinking clock, currently alive in the sense that it still orbits and still transits, currently doomed in the sense that astronomers can already tell you, with real confidence, roughly how many more million years it has left. It is not even the only one caught in this state. A second hot Jupiter, orbiting an aging, expanding star, has shown a similar signature of orbital decay in recent observations. Its transit and eclipse timings shifting in exactly the pattern predicted for a planet losing orbital energy to the star it circles, at a rate suggesting an even faster decline than WASP 12b. Taken together, these are not isolated curiosities. They look like a preview of the same fate that swallowed the planet in Aquila, caught earlier in the process rather than after the fact, which means that somewhere out among the thousands of hot Jupiters cataloged so far, a meaningful fraction may already be living on borrowed time, quietly counting down toward the exact ending that ZTF happened to catch mid-flash. There is a strange kind of comfort, if that is even the right word, in the fact that we can name the specific planet this is currently happening to, watch its transit timing shift by fractions of a second every year, and calculate a rough deadline in millions of years, rather than simply wondering whether such a thing occurs anywhere at all. Most of what this conversation covers tonight is inferred, reconstructed from indirect evidence, built out of chemical fingerprints and statistical surveys. WASP 12b is not inferred. It is simply being watched, transit after transit, its clock visibly running down, in exactly the same sky the rest of these more theoretical worlds share. Somewhere among the stars you can see with an ordinary backyard telescope on a clear night, one of them has a planet already mid-execution, close enough and bright enough that anyone with the right equipment and the patience to keep timing its transits year after year could, in principle, watch the same shrinking pattern for themselves. The physical mechanism behind all of this is, at its core, remarkably simple, even if the consequences are dramatic. A star is not a rigid ball. It is a fluid, and a nearby planet raises tides on it, the same way our moon raises tides in Earth's oceans, bulging the star's surface very slightly toward and away from the planet as it orbits. Because the star does not rotate at exactly the same rate as the planet orbits, those tidal bulges lag slightly behind, and that small offset creates a gravitational torque, a twisting force that very slowly drains orbital energy out of the planet and dumps it into the star as heat. Drain enough orbital energy, and the only place left for the planet to go is inward. The process is agonizingly slow at first, spread across billions of years while the orbit is still comfortably wide, and then it accelerates sharply in the final stretch, because the tidal forces grow stronger the closer the planet gets, in a feedback loop that only tightens as time runs out. That is why a planet like WASP 12b can have already survived for billions of years in roughly its current orbit and still be down to a final few million, a number that sounds enormous until you realize it represents the very last, fastest sliver of a much longer decline that is now essentially finished. There is a specific boundary that governs exactly when this slow spiral turns into a genuine ending, and understanding it makes the whole process feel considerably less mysterious. Every massive body has what astronomers call a tidal disruption boundary, sometimes referred to using the name of the mathematician who first worked out the underlying physics in the 1840s. Inside that boundary, the difference in gravitational pull between the near side of an orbiting body and its far side becomes stronger than the object's own gravity holding itself together, and the object begins to come apart rather than continuing to orbit as a single, intact unit. A planet spiraling inward under tidal decay is, in effect, racing toward that boundary the entire time, and once it crosses it, whatever integrity the planet had left simply gives out. Depending on the planet's own density and composition, crossing that boundary might mean a relatively sudden, catastrophic shredding into a stream of debris that then slowly rains down onto the star over the following weeks or months. Or it might mean, for a sufficiently dense, compact gas giant, that the outer envelope of gas gets stripped away first, while a smaller, denser, rocky, or metallic remnant survives a little longer before finally following the rest of the planet in. Either way, the ending is not really a single dramatic instant so much as the final, fast-acting phase of a process that had already been running quietly for a very long time beforehand. There is something almost uncomfortable about how ordinary this fate turns out to be. Hot Jupiters, gas giants, parked in orbits far tighter than anything in our own solar system, are among the easiest kind of exoplanet to detect, which is exactly why they were among the first kinds of exoplanet ever confirmed back in the 1990s. For years, astronomers studied them as a formation puzzle, wondering how a planet that size ended up orbiting so close to its star in the first place. Since gas giants are thought to form much further out, in colder regions of a young system, and then migrate inward over time. What research over the past decade has slowly made clear is that migrating inward is not where the story ends for many of them. It is only the middle of the story. The same gravitational forces that pulled some of these worlds in close enough to be interesting to astronomers in the first place do not simply stop once the planet settles into a stable-seeming orbit. They keep working, patiently, for as long as it takes, and for a meaningful share of hot Jupiters. The ending they keep working toward is exactly the one already measured for WASP 12b, and already witnessed in full for the planet in Aquila. Astronomers studying this population have started treating orbital decay less as an oddity, confined to one or two famous planets, and more as a predictable stage that a meaningful fraction of hot Jupiters eventually pass through given enough time. Older planetary systems, once surveyed carefully, tend to host noticeably fewer of the tightest, hottest orbiting gas giants than younger systems do, a pattern that fits neatly with the idea that the closest, most vulnerable planets have simply already been consumed by the time a system reaches old age, leaving only the ones that started out slightly further away or arrived on that tight orbit slightly later, still visible in the survey. If that pattern holds up under further study, WASP 12b and its handful of known counterparts are not unlucky exceptions caught at an unusual moment. They are simply the closest, easiest to observe examples of a queue that a large share of hot Jupiters eventually join. There is a third way to find a dead world, and it does not require catching anything in the act at all. It requires reading a kind of forensic evidence, left behind long after the destruction is finished, in the atmosphere of a star that used to be much bigger than it is now. When a star roughly the size of our Sun finally exhausts its usable fuel, it does not explode. It swells into a red giant, sheds its outer layers gently into space, and leaves behind a small, extraordinarily dense core called a white dwarf, typically not much larger than Earth itself, but carrying nearly the full mass of the original star. The physics of a white dwarf's atmosphere is unusually clean and unusually well understood. Because the surface gravity is so extreme, heavy elements like calcium, iron, and silicon should sink out of the visible outer layers within days, leaving behind an atmosphere of almost nothing but the lightest elements, hydrogen or helium, floating on top like oil on water. A white dwarf, left alone, should look chemically simple and stay that way for as long as it exists. And yet, when astronomers examine large samples of white dwarfs, somewhere between 1/4 and 1/2 of them do not look simple at all. Their spectra show clear absorption lines from heavy elements that have no business surviving on the surface for more than a matter of days, and yet there they are. Since those elements cannot have been sitting there since the star's youth, something must be actively feeding them in, recently and repeatedly. The leading explanation, developed and refined over the past 2 decades of research, is that these white dwarfs are still orbited by the remains of a rocky planetary system, asteroids, planetesimals, sometimes entire minor planets, whose orbits get gradually perturbed until they cross too close to the star's crushing gravity and get torn apart by tidal forces, exactly the way a comet passing too close to a star gets shredded into a stream of dust and gas. That shredded material spirals inward in a thin disk, and the star slowly accretes it, 1 grain at a time, contaminating what should be a chemically pure atmosphere with the raw material of a destroyed world. In effect, a polluted white dwarf is a stellar autopsy. Astronomers can read the specific ratios of elements in its atmosphere and reconstruct, in broad strokes, the bulk composition of the object that was ground up to produce them, the same way a forensic chemist can identify what a fire consumed by analyzing the residue left in the ash. The very first hint of this phenomenon was noticed more than a century ago, decades before anyone understood what it actually meant. A nearby white dwarf, identified in the early 20th century and still referred to today by the name of the astronomer who first studied it closely, was found to show clear absorption lines from heavy elements in its spectrum, a genuine puzzle at the time, since the physics explaining why those elements should have already sunk out of sight was not yet fully worked out, and the idea that a dead star might still be actively consuming the wreckage of its own former planetary system was not yet part of anyone's thinking. It took most of a century of slow, accumulating research on the physics of stellar atmospheres, on the discovery of dusty debris disks around other white dwarfs, and eventually on cases like the disintegrating minor planet caught directly in transit, for that single, old, puzzling spectrum to finally make sense as one of the earliest recorded pieces of evidence for exactly the kind of planetary destruction this conversation has been describing. In more than one case, that residue has included oxygen in proportions too high to be explained by ordinary rock alone. Evidence, researchers concluded, that the destroyed body had originally carried a meaningful fraction of water locked inside it before it was torn apart and swallowed. Somewhere out there, in other words, we have already found the chemical remains of what look like drowned worlds, worlds that once carried oceans or ice, later ground into dust and fed into the corpse of their own star. For most of these systems, all we ever get is the aftermath. The dust already spread thin around the star, the destruction already finished. But at least once, astronomers caught the demolition itself, still underway. A white dwarf, catalogued as WD 1145, studied closely after an unusual signal turned up in data from the Kepler spacecraft's extended mission, showed something nobody had ever recorded before. A rocky body still in the process of being shredded, actually transiting in front of the star. The dimming it produced was nothing like the clean, regular dips of a normal planet crossing its star. It was ragged, irregular, changing shape and depth from one orbit to the next, sometimes producing several overlapping dimming events per cycle instead of one, consistent with a disintegrating minor planet, breaking into multiple fragments and trailing long tails of dust and debris behind each piece, the way a comet trails a tail of vaporized ice, except built from vaporized rock instead. Follow-up observations over the following years showed the debris pattern continuing to change, fragments forming, some apparently merging or dispersing, the whole system slowly grinding itself down in real time, close enough and clear enough for astronomers to actually watch the wreckage evolve month by month. Between the quiet chemical fingerprints found in roughly a third to a half of all white dwarfs, and the one system caught mid-collapse with fragments still visibly falling apart, the picture that emerges is not of a rare accident. It looks like an ordinary, almost routine stage in what happens to a rocky planetary system once its star finally ages past the point where it can hold everything together the way it once did. Most planetary systems, this evidence suggests, do not quietly outlive their star. A meaningful share of them get ground down into dust and absorbed by the very same object that built them. There is a strange kind of usefulness buried inside all of this destruction. We cannot fly a spacecraft to most exoplanets. We cannot land a rover on a rocky world orbiting a star 100 light-years away and drill into it the way missions have done on Mars. For almost every rocky planet ever found beyond our own solar system, all we can ever measure directly is its mass and its size, which tells us its average density and not much else about what it is actually made of on the inside. A polluted white dwarf sidesteps that limitation entirely because the star itself has already done the sampling for us. It has reached out, torn a planetary body apart, and displayed the ground-up remains across its own atmosphere where a spectrograph on Earth can read them. In a handful of these systems, Astronomers have identified more than a dozen separate elements in a single white dwarf's contaminated atmosphere at once, enough to reconstruct a rough recipe for the destroyed body, how much iron core it likely had relative to its rocky mantle, whether it carried meaningful water, whether its chemistry looked anything like the rocky planets in our own solar system, or something stranger. It is, in a very real sense, the only place in astronomy where we currently get anything resembling a direct chemical sample of another solar system's rocky planetary material. And every single sample we have came from a world that no longer exists in any recognizable form. That last detail is worth sitting with. Every polluted white dwarf currently being studied for insight into the building blocks of rocky planets is, definitionally, a crime scene rather than a living system. The very evidence that lets us learn the most about what distant rocky worlds are made of is only available to us because those worlds were destroyed first. We are not reading letters from planets that are still standing. We are reading the ash. Scale that fraction up, and the numbers get genuinely hard to hold in your head. Roughly 95% of all stars in the galaxy, including our own sun eventually, are expected to end their lives as white dwarfs rather than exploding as supernovae. The Milky Way is currently thought to contain on the order of 10 billion of them already, the accumulated stellar remnants of over 10 billion years of stars living out their lives and quietly stepping down into this small, dense, final form. If even a conservative reading of the pollution statistics holds across that entire population, a meaningful fraction of 10 billion separate stellar systems have each, individually, ground up at least one rocky world and fed the remains into their own dying star. That is not a handful of unlucky planets. That is a routine, built-in stage in the life cycle of a rocky planetary system, repeated across a number of stars too large to comfortably picture, playing out continuously across the galaxy for as long as stars have been aging into white dwarfs at all. The variety hidden inside these polluted atmospheres is itself worth pausing on. Not every contaminated white dwarf tells the same story. Some show a composition heavy in iron and nickel, consistent with the destruction of a body that had already differentiated into a dense metallic core surrounded by a lighter rocky mantle, essentially the wreckage of something that once looked, internally, something like Mercury or Earth. Others show a composition dominated by lighter rocky material with comparatively little metal, more consistent with the crust or mantle layers alone, without much of the core mixed in, suggesting either a smaller, undifferentiated body or the outer layers of a larger one that had its metallic heart stripped away and lost separately. A handful of especially rare cases show unusually high levels of carbon, hinting at destroyed bodies with an entirely different bulk chemistry than any of the rocky planets in our own solar system, built from a recipe that never had a direct analog here. Reading through enough of these polluted spectra starts to feel less like studying one repeated kind of destruction, and more like flipping through an entire, varied catalog of different planetary recipes, each one known to us only because it was eventually ground apart and swallowed. A white dwarf is not the only kind of star that can carry a chemical record of a destroyed planet. Ordinary, still-living stars, stars very much like our own sun, can carry a version of the same evidence, and finding it depends on a much stranger kind of comparison. Stars that form together, out of the same collapsing cloud of gas at the same time, are expected to share almost exactly the same original chemical makeup, since they were built from the same raw material. This is especially true of binary star pairs, two stars orbiting each other, born side by side from the same cloud. If everything about planet formation happened identically for both stars in a pair like this, their chemical compositions today should still match closely, element for element. Astronomers who study what they call solar twins, stars chemically almost indistinguishable from our own sun, have used exactly this expectation to go looking for evidence of destroyed planets in stars that are still very much alive. What some of these studies have found, when comparing binary pairs of otherwise near-identical twin stars, is a small but real difference in the abundance of certain elements, specifically the kind of heavy, rock-forming elements like iron, silicon, and other refractory metals that would have been locked up inside any rocky planets, asteroids, or planetesimals that once orbited that star. In several documented cases, one star in a pair shows a modest excess of exactly these elements compared to its twin, an excess too specific and too selective to be explained by ordinary differences in how the two stars formed. The leading explanation is that the enriched star, at some point in its history, absorbed rocky material, an asteroid belt disrupted and driven inward, a failed planet that never stabilized into a safe orbit, or even a small rocky planet outright, swallowing material that quite literally salted its outer atmosphere with the same elements that would have made up that destroyed body's crust and mantle. This matters because it means the destruction described throughout tonight is not confined to the exotic, extreme stellar remnants like white dwarfs and pulsars. It appears to leave a legible mark even on perfectly ordinary, still hydrogen-burning, still comfortably middle-aged stars, stars in the same broad category as our own sun. A star does not need to die, expand into a red giant, or collapse into a stellar corpse to have already consumed part of its own planetary family. Some of it can happen quietly, early, while the star and whatever remains of its planetary system are still going about their ordinary lives, leaving behind nothing more dramatic than a faint chemical fingerprint, detectable only by astronomers patient enough to find a nearly perfect twin star to compare it against. The precision this kind of study demands is worth appreciating on its own terms. The chemical differences researchers are hunting for between two twin stars are extremely small, often only a few percent difference in the abundance of a given element relative to hydrogen, a signal easily buried under the ordinary measurement uncertainty of a standard spectroscopic analysis. Confirming a genuine, planet-related difference, rather than simple observational noise, requires extraordinarily high-resolution spectroscopy, careful, repeated observations of both stars under closely matched conditions, and statistical techniques sensitive enough to separate a real, physical signal from the ordinary scatter every measurement carries with it. This kind of work has only become routinely possible with the newest generation of high-precision spectrographs built over roughly the past 15 years, meaning the technique itself is nearly as young as several of the other detection methods covered tonight, part of the same broader wave of improving instruments that has turned what used to be theoretical speculation about planetary destruction into a genuine, actively growing, observational field. Not every destroyed world needed a star to do the destroying. Sometimes the danger came from another planet. Planet formation does not end neatly. Long after a star ignites, and a disk of gas and dust begins clumping into larger and larger bodies, the inner region of a young system is typically still crowded with dozens of planetary embryos, roughly Moon to Mars-sized objects, all sharing similar orbits, all tugging at each other's paths. Over tens of millions of years, some of those orbits cross. When two bodies of that size collide, the result is not a gentle merger. It is a genuine hypervelocity impact, releasing enough energy to melt and vaporize enormous quantities of rock in an instant, throwing a portion of both bodies into orbit as a glowing cloud of debris, rather than leaving it safely attached to either survivor. We are not simply guessing that this happens based on our own solar system's early history. Astronomers have found direct evidence of it happening around other stars caught in progress. around a young star called HD 17255, roughly 100 light-years away and only a few tens of millions of years old. Observations picked up an unusual amount of fine, glassy silica dust, along with hot silicon monoxide gas surrounding the star, a specific chemical signature that does not match the ordinary leftover material from planet formation. It matches, instead, the kind of vaporized, shattered rock produced by a genuine hypervelocity collision between two large, differentiated planetary bodies, essentially the aftermath of a collision similar in scale and violence to the one that is thought to have shaped our own Earth and Moon, caught as a snapshot of debris rather than an event anyone actually witnessed happening. An even more direct case turned up around a young, sun-like star roughly a few 100 million years old, part of a stellar cluster studied repeatedly with an infrared space telescope over several years. Observations taken a few years apart showed a large, previously undetected cloud of warm dust had appeared where nothing had been seen before, then began fading again over the following years, consistent with exactly the kind of short-lived debris cloud a major collision between two planetary-sized bodies would produce, watched not in the act of the impact itself, but in the glowing aftermath, rising and then settling. The closest thing astronomers have to a time-lapse photograph of a planet-sized collision happening around another star. Our own solar system carries at least one planet that looks like it survived precisely this kind of violence rather than avoiding it. Mercury, the innermost planet, is strange in a specific, measurable way. Its metallic iron core takes up roughly 85% of the planet's entire radius, an enormous fraction compared to the other rocky planets, where the core typically accounts for something closer to half the radius or less. The leading explanation for Mercury's oversized core is that the planet originally formed with a far more ordinary ratio of rocky mantle to metal core, and then, early in the solar system's history, suffered a glancing but immensely violent collision that stripped away a large share of its outer rocky material, blasting it away into space or into the sun, and leaving behind a planet that is now mostly the surviving metallic heart of something considerably larger. Mercury, on this account, is not simply a small planet. It is the leftover core of a bigger one. And there is a version of this story even closer to home than that, close enough that you are, in a real sense, standing on the evidence of it right now. The leading explanation for how Earth's moon formed involves a collision between the young Earth and a planetary body roughly the size of Mars. Sometime in the first 100 million years after the solar system formed, the impact was violent enough to melt a substantial portion of both bodies, throwing a ring of vaporized rock and debris into orbit around what remained of Earth, material that gradually cooled, clumped together, and became the Moon. Earth itself survived that collision, reshaped and reset by it rather than destroyed. But the object that struck it did not survive at all, at least not as a separate planet. It became part of Earth, part of the Moon, and in a very literal sense, part of the iron in Earth's own core today. The planet you are standing on carries, inside it, the remains of another planet that no longer exists in any form except as a fraction of this one. One additional case is worth telling on its own, because it involves a planet that astronomers once believed they had actually photographed directly, only to watch it disappear. Around the bright, nearby star Fomalhaut, roughly 25 light-years away, a faint point of light was first captured in images from the Hubble Space Telescope in the middle of the 2000s, and announced at the time as one of the first visible light photographs ever taken of a planet orbiting another star. Follow-up observations over the following years complicated that story considerably. The object was fading over time, growing fainter and more spread out, rather than staying compact and steady the way a real planet should, and its motion looked more consistent with material, slowly drifting apart on an escaping path than with a stable planetary orbit. By the following decade, most researchers studying the system had concluded it was never a planet at all, but an expanding cloud of fine dust thrown out by a collision between two large planetesimals, roughly comet or dwarf planet-sized bodies, sometime shortly before the first images were taken. Then, in a final twist, when astronomers checked the same spot again in the following years, the original point of light had vanished entirely, and in its place, at a slightly different position, a brand new point of light had appeared, consistent with a second, separate collision having happened in the very same debris belt. What was once celebrated as humanity's first photograph of an alien world quietly turned into something arguably more interesting. Direct, repeated photographic evidence of planetary bodies being smashed apart, one after another, in the same distant ring of debris. Put together, these pieces of evidence, a young star's collision debris still glowing in infrared, a fading dust cloud caught rising and settling around another young system, a photographed planet that turned out to be two successive collisions in the same debris belt, and two of our own solar system's rocky worlds carrying the physical scars of exactly this kind of violence, suggest giant impacts are not a rare accident restricted to our own early history. They appear to be an ordinary, almost expected stage that a large share of young rocky planetary systems pass through on the way to whatever quieter, more settled configuration eventually survives. Some worlds involved in that stage keep going afterward, reshaped rather than destroyed. Others do not survive as separate objects at all, and simply become raw material folded into whichever neighbor happened to hit them hardest. None of this evidence would exist at all without a specific, fairly recent advance in how astronomers actually look at other star systems. For most of the history of this field, a planet or a debris disk around another star was simply too faint and too close to its own blindingly bright host star to see directly at all, drowned out by starlight the way a candle flame would be drowned out by a searchlight sitting right beside it. Specialized instruments called coronagraphs, which physically block out the light of the central star inside a telescope, along with a growing network of radio observatories capable of resolving the faint glow of cold dust at wavelengths where the star itself is comparatively dim, have only become good enough to routinely image these debris disks and their internal structure within roughly the past 2 decades. Every ring, gap, warp, and asymmetric clump found inside a debris disk around another star, the kind of feature that reveals an embedded planet clearing a lane through the dust, or a recent collision throwing a fresh, localized cloud into an otherwise smooth ring, is a discovery that simply was not possible to make with the instruments available 1 generation earlier. The universe was not more violent 20 years ago than it is today. We were only recently given eyes sharp enough to actually watch it. Our own solar system carries a quieter, closer version of this same ongoing collisional grinding, one that has simply been running for so long it no longer produces the kind of dramatic, headline-making event that a fresh collision around a young star does. The outer solar system beyond Neptune holds an enormous, thinly scattered population of icy bodies left over from the earliest days of planet formation, a region that has been slowly, continuously colliding and fragmenting for the entire 4.5 billion year history of the solar system. Every short period comet currently visible from Earth is, in a real sense, a small piece of that ancient, ongoing grinding process, a fragment knocked loose from a larger parent body sometime in the deep past and sent falling inward on a long, looping orbit that eventually brings it close enough to the sun to grow a visible tail. Space missions that have flown close enough to photograph these bodies directly, rather than only observing them from a great distance, have returned images of oddly shaped, elongated, sometimes double-lobed structures, consistent with slow, gentle mergers between smaller bodies early on, layered on top of a much longer history of subsequent collisions, chipping pieces away again afterward. The same basic process responsible for the dramatic, freshly imaged debris clouds around young stars light years away has simply been running quietly in our own backyard the entire time, at a pace slow enough and in a region dim enough that it rarely makes the news, but never actually stopped. There is one case in all of this that runs the story backward, and it deserves a place here precisely because of that. A pulsar is what remains after a massive star ends its life in a supernova, one of the most violent events a star can undergo. Its core collapsing down into an object barely wider than a city, spinning many times per second, and sweeping a beam of radiation across space like a lighthouse with every rotation. Whatever planets happened to be orbiting that star before it exploded should not have survived the event. A supernova blasts away a huge fraction of the star's remaining mass in a matter of seconds, releases more energy than the star produced across its entire prior lifetime combined, and floods the surrounding space with exactly the kind of intense radiation this conversation has already described as capable of sterilizing or destroying a planet from tens of light years away. Delivered here from essentially point-blank range, any planet in a system like that should, by every reasonable expectation, be gone. And yet, in the early 1990s, in one of the genuinely strange turns in the whole history of exoplanet science, astronomers confirmed the presence of planets, several of them, orbiting a pulsar. It was, in fact, the very first confirmed detection of planets around any star other than our own, arriving years before the first confirmed planet around an ordinary, still living, main sequence star. The method that found them was as strange as the discovery itself. Astronomers were timing the pulsar's radio beams sweeping past Earth with extraordinary precision, expecting a perfectly steady rhythm, and instead found tiny, regular variations in the timing, caused by the gravitational tug of unseen planets pulling the neutron star very slightly back and forth as they orbited it. The leading explanation for how planets could possibly exist around an object that had so recently detonated as a supernova is not that the original planets somehow survived the explosion. It is that they did not, and that what we are seeing now is a second generation. In the aftermath of a supernova, debris that failed to escape the newly formed neutron star's gravity can fall back and settle into a disk of gas and shattered material encircling the fresh stellar corpse, essentially a new, miniature version of the same kind of disk that builds planets around any young star. Given enough time, roughly the same physics that builds planets around any ordinary young star can begin operating again in that fallback disk, clumping material together, building up rocky bodies, eventually producing planets orbiting an object that, strictly speaking, already destroyed an earlier planetary system to create the very material those new planets are built from. What makes the original detection especially remarkable, beyond the strangeness of the underlying story, is just how precise the measurement had to be. A pulsar's radio beam sweeps past Earth with a regularity that rivals or exceeds the best atomic clocks built by human engineers, and the tiny gravitational nudge from a small rocky planet only shifts that timing by an amount measured in fractions of a thousandth of a second. Detecting planets this way required years of continuous, extraordinarily precise timing observations, patient enough to notice a wobble in the pulsar's rhythm, so small that almost any other kind of measurement would have simply treated it as noise. It remains, even decades later, one of the most sensitive planet detection methods ever used, ironically capable of finding smaller planets in some respects than many of the techniques developed afterward, specifically to search for planets around ordinary, living stars. Sit with that sequence for a moment, because it runs directly against almost everything else covered tonight. Every other mechanism in this conversation describes a planet or a planetary system ending permanently, with nothing meaningfully replacing it. Pulsar planets describe an ending so severe it erased an entire star system, immediately followed by new planets rising directly out of the wreckage that ending produced. The destruction, in this one case, was not simply the end of the story. It was the raw material for a new one, assembled in the debris field of the very event that should have made planet formation there impossible. It would be tempting to read that as some kind of comforting counterweight to everything else this conversation has covered. Proof that construction always eventually follows demolition, that nothing is ever permanently lost, only recycled. The truth is narrower and stranger than that. Pulsar planets are not a promise that destruction reverses itself. They are a demonstration that the same universe capable of tearing a planetary system apart through a supernova is also, separately, capable of building an entirely new one out of what is left over, when the conditions happen to allow it. Whatever planets orbited that star before its supernova are gone completely, with no version of them continuing forward in any form. What orbits there now are strangers, born afterward, in a very literal sense, living on a former grave rather than surviving as a resident of it. Not every dead world gets swallowed whole or ground into dust. Some simply lose the one thing that made them interesting in the first place. Their atmosphere boiled off, a little at a time by their own star, until nothing is left but bare, naked rock. Young stars are far more energetic in their first few 100 million years than they will ever be again. They flood the space around them with extreme ultraviolet light and X-rays, radiation intense enough to physically heat the outer atmosphere of any nearby planet until the gas itself is moving fast enough to simply escape, molecule by molecule, into space. For a planet orbiting close to its star, this process, called photoevaporation, can strip away an entire primordial envelope of hydrogen and helium within the first billion years of the planet's existence. The evidence for this shows up clearly once you have surveyed enough planets to compare them. Among the thousands of confirmed worlds cataloged so far, there is a strangely empty gap in the data. A size range, roughly between 1.5 and 2 times the radius of Earth, where far fewer planets exist than the surrounding sizes would predict. Astronomers call it the Radius Valley. On one side of that gap sit planets that manage to hold onto a puffy envelope of hydrogen and helium, sometimes called mini-Neptunes, larger and lower in density than a bare rocky world of the same mass. On the other side sit planets that lost that envelope entirely, leaving behind compact, dense, rocky worlds, sometimes called super-Earths. The gap between them is not a coincidence of formation. It looks like the direct fingerprint of radiation stripping planets down over time. Some kept enough gravity and enough distance from their star to hang on to their atmosphere, and some did not, and ended up on the other side of the valley, naked. For some worlds, this stripping process is not even finished yet, and it is violent enough to watch directly. A handful of small, rocky planets have been found orbiting so close to their star, with orbital periods measured in mere hours rather than days, That starlight is not just stripping a lingering hydrogen envelope, it is heating the actual rock and mineral surface of the planet past its melting point, vaporizing solid material directly off the day side and pushing it into space in a visible trailing cloud of dust, observed from Earth as an irregular, ever-changing dimming pattern with each orbit, sometimes deeper, sometimes shallower, because the amount of dust the planet sheds is not the same from one pass to the next. These are, functionally, planets actively boiling away in front of our instruments, worlds so close to their star that the ordinary distinction between rock and atmosphere has broken down entirely, and every single orbit removes a little more of the planet than the orbit before it. Put the radius valley and these actively evaporating worlds together, and a pattern emerges that has nothing to do with violence in the dramatic sense of an explosion or a collision. It is slower than that, and in some ways stranger. It is a planet simply being worn away, breath, by the same star that gave it warmth in the first place, until either it settles into a smaller, harder, permanently altered version of itself, or in the most extreme cases, until there is measurably less of it with every year that passes. There is a companion pattern in the data that tells a similar story from a different angle. Among the giant planets discovered so far, there is another conspicuous gap, this time in orbital distance rather than size, a range of very short orbital periods, of only a few days, where fewer sizable gas planets are found than the broader population would predict. Researchers have taken to calling it the hot Neptune desert, and the leading explanation reads almost identically to the Radius Valley story. A gas planet that strays into that close, scorching territory either has enough mass and enough gravity to hold onto its atmosphere against the radiation pouring off the star, or it does not. And if it does not, the atmosphere strips away fast enough that the planet effectively cannot survive there in its original form for long. What is left behind? On the rare occasions researchers do find something sitting inside that supposed desert, tends to be a smaller, denser leftover core, the stripped remains of what used to be a much larger world before its outer layers were carried away. Surveys built specifically to detect planets, first from the Kepler spacecraft and later expanded by its successor missions, were never designed to find the planets that used to exist and no longer do. They can only measure the planets that happen to still be there at the moment we look. Every gap in the size and orbit statistics, the Radius Valley, the hot Neptune desert, is therefore not really a gap in what the universe originally built. It is a gap in what survived being built that close to a star, a quiet census of an absence, drawn entirely from counting what is missing rather than what is present. The Radius Valley itself was only firmly established as a real, statistically solid feature of the exoplanet population within roughly the past decade. Once the Kepler mission had accumulated enough precisely measured planet sizes across enough stars to separate a genuine gap from ordinary statistical noise. Before that, individual planets scattered across the size range now known to be sparse were simply treated as unremarkable data points, no different from any of their neighbors. It took the accumulated weight of thousands of individually unremarkable measurements, compared carefully against each other, to reveal that a specific, narrow slice of planetary sizes was quietly underpopulated across the entire survey. That is itself a useful lesson about how this kind of destruction tends to get discovered. It rarely announces itself as a single dramatic event. It shows up first as an absence, a strangely empty patch in an otherwise smooth distribution, noticed only once enough individual. Unremarkable data points have piled up for the shape of what is missing to finally become visible. The James Webb Space Telescope has started checking this story planet by individual planet rather than only statistically. Small, rocky worlds orbiting close to cooler, smaller stars are some of the easiest rocky planets to examine this way, because the contrast between a small star and a small planet is more favorable than it is around a star like our own Sun. When astronomers have pointed Webb at several of the nearest, best-studied examples, hoping to detect a thick atmosphere the way Earth or Venus would show one, more than one of them has come back looking essentially bare, showing no clear sign of holding onto any meaningful blanket of gas at all. That does not necessarily mean every rocky planet around every small star ends up the same way. It does mean that the Radius Valley and the hot Neptune Desert are not only patterns hiding in a spreadsheet of statistics somewhere, they are showing up, one confirmed case at a time, as individual bare worlds checked directly and found wanting. One of the very first exoplanets ever found, a gas giant discovered in the closing years of the last century, orbiting a sun-like star only a comfortable distance away, became the first planet beyond our own solar system, where astronomers directly measured atmosphere, physically escaping into space, rather than simply inferring the loss statistically from a population of planets afterward. Observations using ultraviolet light, sensitive to hydrogen absorption, revealed that the planet is surrounded by an enormous, extended envelope of escaping hydrogen gas, streaming away from the planet under the pressure of intense stellar radiation, forming a comet-like tail that trails behind the planet in its orbit and reaches a size many times larger than the planet itself. Follow-up studies later found helium escaping in a similar fashion from other close-orbiting gas giants, confirming that this kind of active, ongoing atmospheric bleed is not a one-time fluke, but a genuine continuing process happening to more than one planet, currently sitting in easy reach of our telescopes. These are not planets that used to have more atmosphere at some point in the ancient past. They are planets you can point an instrument at during this decade and watch losing material right now, mid-breath, so to speak. In the astronomical present tense, rather than only in the deep past tense, every other mechanism in this conversation mostly requires. Two specific worlds deserve to be named directly here, because they are not statistical inferences drawn from a gap in a chart. They are individual, confirmed planets that astronomers have watched come apart, transit after transit, for well over a decade now. The first was found by the original Kepler mission, orbiting its star in less than a single day, a planet small enough and close enough to its star that its surface temperature is thought to sit somewhere around 2,000 degrees Celsius, hot enough to keep at least part of its dayside as an ocean of molten rock rather than solid ground. What caught astronomers' attention was not the planet itself, which is far too small and far too dim to see directly, but the shape of the dip it produces every time it crosses in front of its star. An ordinary transiting planet produces a clean, symmetrical dip that looks essentially the same orbit after orbit, because the planet's shape and size do not change. This one does not. Its transit depth varies noticeably from one orbit to the next, sometimes deep, sometimes shallow, and the shape of the dip itself is lopsided, fading in gradually and then recovering more slowly afterward. Exactly the signature you would expect from a solid body trailing a long, drifting tail of dust behind it. The same basic geometry as a comet's tail, except made from vaporized and recondensed rock boiling directly off a planetary surface rather than ice. A second, independently confirmed example was found years later using the Kepler spacecraft's extended second mission, orbiting a different star on an even shorter period, and showing the same basic behavior, a variable, asymmetric transit, consistent with an actively shedding dust tail. Follow-up observations of both systems, spread out over multiple years, have shown the dimming pattern continuing to change over time, sometimes producing a noticeably larger dust cloud in one observing season than another, evidence that the rate of material being lost is not steady. It ebbs and spikes, the way a coastline erodes faster during some storms than others. The physical picture behind both of these worlds is about as extreme as planetary science currently gets. Daytime temperatures hot enough to vaporize rock directly turn solid mineral into gas at the surface, which then recondenses into fine dust grains as it rises and cools slightly away from the hottest region. And radiation pressure from the star pushes that fresh dust backward into a visible trailing tail, the same way sunlight pushes the dust tail of an ordinary comet away from the sun. Every single orbit, in other words, both of these planets lose a measurable sliver of their own mass into space as a fine mineral haze, and every single orbit that same mass never comes back. Current estimates suggest planets like this could lose enough material to disappear entirely, reduced from a full-size planet down to nothing at all, within a span of a few 100 million years, an ending that is genuinely, actively in progress right now, rather than a distant hypothetical. There is something almost unsettling about how visible this particular kind of death actually is, compared to almost everything else covered tonight. A rogue planet drifting through interstellar darkness cannot be seen directly at all. A polluted white dwarf shows only chemical residue long after the fact. These two disintegrating worlds are different. Their deaths show up as a direct, repeating, measurable signal, recorded transit after transit, year after year, in publicly available survey data that anyone with the right tools could go check for themselves. It is, in its own strange way, one of the most openly documented planetary deaths currently known, precisely because the planet in question is dying slowly enough and regularly enough for us to keep watching. There is a reasonable question worth asking directly here, which is how something this extreme was ever confirmed, rather than dismissed as an instrument glitch or a background contaminant in the data. The answer comes down to persistence and repetition. A single unusual dip in a star's brightness could plausibly be almost anything. A passing asteroid unrelated to the star, a star spot rotating into view, a brief instrumental error. What convinced astronomers that they were looking at a genuine, physically disintegrating planet rather than any of those alternatives was the fact that the irregular, variable dimming kept recurring on the same orbital period over and over, across years of continuous monitoring, always roughly in the same place in the orbit, even as the exact depth and shape of each individual dip kept shifting. That combination, a signal locked to a stable orbital period but variable in its precise details from one pass to the next, is very difficult to produce with anything other than a real object in a real orbit that is actively losing a changing amount of material on each trip around its star. Once enough individual transits had been collected and compared against each other, the disintegrating planet interpretation became by far the simplest explanation left standing, and it has held up under every subsequent round of scrutiny and additional observations since. Every world we have talked about so far met its end through something local, its own star, its own orbit, its own gravity working against it. But a planet does not just belong to a star system. It belongs to a galaxy, and a galaxy is not an evenly gentle place to sit in for billions of years. A supernova is the explosive death of a massive star, and on the scale of an entire galaxy, it happens often, roughly a couple of times per century in a galaxy the size of the Milky Way. Most of them go off harmlessly far away. But a supernova detonating within, somewhere around a few tens of light years of an inhabited planet, is close enough to matter directly. The burst of radiation it releases can strip away a meaningful fraction of a planet's protective ozone layer within days. letting through enough ultraviolet light to damage surface life and disrupt the base of a food chain that depends on photosynthesis. Some researchers have proposed that a nearby cosmic explosion, whether a supernova or a shorter, even more intense gamma ray, burst from a different kind of stellar collapse, may already have reached into Earth's own deep history at least once, contributing to one of the more severe extinction events in the fossil record, though that link remains a hypothesis rather than settled fact. A gamma-ray burst is a far more extreme, far more tightly focused event than an ordinary supernova, capable of delivering the same kind of ozone-destroying dose of radiation from thousands of light-years away, but only along a narrow beam, meaning most planets in a galaxy are never in the line of fire, and a small, unlucky number are directly in it. Zoom out from any single explosion, and a broader idea starts to take shape, one astronomers call the galactic habitable zone. The concept works a lot like the habitable zone around an individual star, except applied to an entire spiral galaxy instead of a single star system. Close to the crowded, violent center of a galaxy, stars are packed tightly together, supernovae go off more frequently, and the chances of a planet eventually sitting too close to one of these events climb steadily higher over billions of years. Far out toward the edge of a galaxy's disk, the danger from nearby explosions drops, but so does something else a rocky planet actually needs: heavier elements like carbon, oxygen, and iron. The raw material rocky worlds and their potential chemistry are actually built from, which are far more abundant in a galaxy's inner and middle regions, seeded there generation after generation by earlier stars living and dying. The galactic habitable zone is the compromise band between those two pressures, not too close to the violence, not too far from the raw material, and depending on which model you use, it may only cover a modest fraction of a spiral galaxy's total volume and total stellar population. None of this changes anything about whether a specific planet's own chemistry, orbit, or star are cooperative. It sits underneath all of that. As a separate filter, a world has to pass through purely by virtue of its address inside the galaxy. Our own solar system happens to sit out in a relatively quiet stretch of one of the Milky Way's spiral arms, far enough from the crowded galactic core that nearby supernovae are a rare rather than a routine hazard. That placement was never something Earth earned. It is closer to an accident of where the cloud of gas that eventually became our solar system happened to be drifting 4.5 billion years ago, when it finally collapsed into a star and its planets. Move the same solar system a few thousand light-years closer to the galactic center. Keep every other detail about Earth identical, and its odds of having already been irradiated into sterility at some point over 4 billion years climb by a real, measurable amount. Geography, on the scale of an entire galaxy, turns out to matter almost as much as chemistry. The most extreme version of a hostile galactic neighborhood is not even inside the disk of the Milky Way at all. Globular clusters, tightly packed spherical swarms of hundreds of thousands of ancient stars, orbiting the galaxy as a whole in a wide halo above and below its flattened disk, pack their member stars far closer together than anywhere in our own comparatively spacious neighborhood. Sometimes, with neighboring stars, separated by distances smaller than the gap between our own sun and its nearest stellar neighbor by a wide margin. In an environment that crowded, close, stellar encounters capable of directly disturbing or stripping away a planet's orbit are dramatically more frequent, and searches for planets inside globular clusters have so far turned up remarkably few confirmed detections, despite the enormous number of stars available to search. Whether that scarcity reflects planets that never had the chance to form properly in such a crowded, gravitationally turbulent birth environment, or planets that formed normally and were later torn loose or destroyed by the sheer density of stellar traffic around them, remains an open question. Either way, it is a useful reminder that the galactic habitable zone is not simply about distance from the core in a flat, two-dimensional sense. It is about the full three-dimensional structure of an entire galaxy. And some regions of that structure, dense clusters most of all, appear to be almost uniformly unfriendly to the whole project of building and keeping a stable planetary system together. There is a slower, quieter version of this same hazard, one that does not require any single dramatic explosion at all. Our solar system does not sit still relative to the rest of the galaxy. It orbits the galactic center roughly once every couple of 100 million years, drifting slowly up and down and in and out relative to the busier, denser regions of our own spiral arm as it goes, occasionally passing through or near denser clusters of stars and gas that it is not normally close to. Some researchers have proposed that these periodic crossings could nudge distant comets loose from the solar system's outer edge more often than usual, sending an elevated number of icy bodies down into the inner solar system over spans of a few million years, though the strength of that particular link is still debated. One specific case makes this less abstract. A small, dim, binary pair of stars, now generally referred to by the name of the astronomer who first identified its unusual motion, is calculated to have passed remarkably close to our own solar system, well within the outer edge of our Oort cloud, somewhere around 70,000 years ago, a span of time well after modern humans already existed, though long before any recorded history. The pass was close enough, astronomically speaking, that its gravity plausibly nudged at least some small icy bodies loose from their long, slow orbits far beyond Neptune, sending an unknown number of them drifting inward on new paths. Nothing about that particular flyby caused any noticeable damage to Earth as far as anyone can tell. It was simply close enough to leave a fingerprint in the orbital statistics of the outer solar system, a quiet reminder that other stars do, in fact, wander close enough to physically disturb a planetary system every so often, on timescales far shorter than the age of the galaxy itself. Whether or not the broader comet shower mechanism holds up, the broader point stands on its own. A planet's exposure to danger is not fixed once at the moment of formation. It keeps shifting slowly across a world's entire history as the star system it belongs to carries it through different neighborhoods of the same galaxy over hundreds of millions of years, some quieter, some considerably less so. This is also, quietly, one of the reasons search efforts, looking for signs of other civilizations, tend to weight certain regions of the sky more heavily than others. A civilization trying to survive long enough to be noticed needs more than a stable star and a well-placed planet. It needs a stable neighborhood for a very long time, which is a much harder thing for any single world to guarantee than it might first appear. There is a further wrinkle here that is easy to overlook, which is that a galaxy's overall hazard level has not stayed constant across its own history either. Earlier in the life of the Milky Way, when the disk was younger and star formation rates were higher, supernovae were going off considerably more often across the galaxy as a whole than they are today, since more massive, short-lived stars were being born and dying at a faster clip. That means any planet old enough to have existed during the galaxy's more turbulent early centuries faced a meaningfully higher background hazard rate than an equally placed planet forming today would face, simply because it was unlucky enough to arrive earlier in the galaxy's own history rather than later. Our own solar system, forming roughly 9 billion years after the galaxy itself first began assembling, arrived comparatively late to a Milky Way that had already calmed down considerably from its noisier youth. A planet identical to Earth in every other respect, but built a few billion years earlier during a rowdier phase of galactic history, would have faced a meaningfully higher chance of encountering a nearby supernova at some point across its own multi-billion-year lifetime, purely as a matter of unlucky timing rather than unlucky placement. There is one more layer of protection worth naming, because it shows just how many separate things have to hold up at once for a planet to stay safe. Every star blows a constant outward wind of charged particles, and that wind inflates a vast bubble around the whole system, called a heliosphere. Or in the case of another star, an astrosphere, which acts as a kind of first line of defense against the more energetic radiation drifting through interstellar space between stars. A star that is unusually quiet, aging, or simply weaker than average produces a smaller, thinner bubble of this kind, offering its planets noticeably less shielding from the wider galactic environment than a more vigorous star would. A planet can therefore have every other ingredient in place: a stable orbit, a strong magnetic field of its own, a comfortable distance from its star, and still end up more exposed than it should be, simply because the star protecting it from the outside is not doing its share of the work as effectively as ours currently does. That bubble is also not a fixed size for our own solar system either. It shrinks when the surrounding interstellar material happens to be unusually dense, and there is physical evidence, preserved in the form of a specific radioactive isotope found in deep-sea sediment and in lunar soil, suggesting our own solar system may have drifted through one or more denser interstellar clouds at some point over the last several million years, an era when the heliosphere would likely have offered somewhat less shielding than it does comfortably today. Nothing catastrophic appears to have followed from it, at least nothing yet identified in the fossil or geological record. But it is a reminder that even the protective bubble a star wraps around its own planets is not a constant, guaranteed feature of a system. It flexes with the neighborhood. The whole system happens to be passing through at any given point in its multi-billion-year journey around the galaxy. There is one more source of destruction worth understanding, because it connects almost everything we have already covered tonight back into a single loop. Most stars in this galaxy are not alone. Somewhere close to half of all sun-like stars belong to binary or even triple star systems, 2 or 3 stars bound together by gravity, orbiting a shared center of mass rather than sitting solo the way our own sun does. A planet forming in a system like that inherits a much more complicated gravitational environment than a planet forming around a single star. Instead of one steady source of gravity to settle into orbit around, it has to contend with the shifting, combined pull of 2 or more massive bodies, each one tugging at its orbit in a slightly different direction, as the stars themselves swing around each other. For an orbit to remain stable over billions of years in a system like this, a planet generally needs to sit either very close to just one of the stars, tucked in tightly enough that the second star's pull barely matters, or very far out from the whole pair, orbiting the entire binary system as a single distant point of gravity. The middle ground, orbits at intermediate distances where a planet feels a serious, competing pull from both stars at once, tends to be dynamically unstable, sometimes over a few thousand years. Sometimes only after millions of years of accumulating small nudges finally add up to something decisive. Simulations built to study exactly this problem consistently find that a large share of planets that start out in these unstable middle orbits do not stay in the system at all. As the competing gravity from both stars slowly pumps energy into the planet's orbit, it can eventually be flung out entirely, achieving enough speed to escape the whole system for good, joining the same population of starless, drifting rogue worlds discussed earlier tonight. In some studies of tightly interacting binary systems, ejecting at least one planet turns out to be closer to the expected outcome than the exception, particularly for planets that formed on tilted or misaligned orbits relative to the two stars they were born around. This matters because it means the rogue planet population, the free-floating jumbos, and the individually confirmed drifting worlds detected through microlensing are not simply the leftovers of single star systems that had one clumsy accident during formation. A meaningful fraction of them may be the direct product of binary and triple star systems working exactly as gravitational physics predicts they should, sorting their planets into the ones close enough to survive, the ones far enough out to survive, and the ones caught in between that eventually get thrown away entirely. Multiply that sorting process across the roughly half of all stars living in these multiple star systems. Repeat it over billions of years across the whole galaxy, and the population of ejected, homeless worlds stops looking like a strange edge case. It starts looking like one of the ordinary, predictable outputs of how a large fraction of planetary systems are built in the first place. Not every planet in a binary system loses this particular gamble, which is exactly why the survivors are worth naming too. Astronomers have confirmed several planets that orbit both stars of a binary pair at once, sitting comfortably out beyond the reach of the destabilizing middle zone, circling the entire pair the way a single distant point of gravity would be circled. One of the earliest and most famous examples, found by the Kepler spacecraft, orbits its two parent stars closely enough in the sky that, from its own surface, an observer would see two suns rise and set together, sometimes overlapping, in a scene that looks almost too much like something out of a film rather than a real, measured planetary system. These circumbinary survivors prove that the wide, stable orbits genuinely exist and genuinely hold. They are not just a theoretical safe zone on paper. They also make the losses easier to see clearly by comparison, because for every planet found comfortably orbiting a binary pair from a safe distance, simulations suggest a considerably larger number of siblings, born in the same system, on the same disk of gas and dust, never made it to a stable orbit at all. Finding these circumbinary survivors at all required years of exceptionally patient observation, precisely because a planet orbiting two stars produces a far messier signal than a planet orbiting one. Instead of a steady, perfectly repeating transit interval, the timing and duration of each dip in starlight shifts noticeably from one crossing to the next. Since the planet is not tracing a simple, unchanging path relative to a single fixed point of light, it is threading a more complicated route around two separate, orbiting sources of light at once. Confirming even a single circumbinary planet typically required several years of continuous monitoring before the pattern became clear enough to rule out other explanations. Out of the full Kepler mission's multi-year survey of well over 100,000 stars, only a small handful of these confirmed circumbinary systems have emerged, a scarcity that is at least partly an artifact of how difficult they are to detect and confirm, and at least partly, most researchers suspect, a genuine reflection of how few planets actually survive long enough in the right kind of orbit to be found this way in the first place. Even the nearest star system to our own carries this same open question. Alpha Centauri, a bright triple star system only a handful of light-years away, has been searched repeatedly for planets, with only tentative, unconfirmed hints turned up so far rather than a clear detection. Some of that difficulty is simply the technical challenge of detecting a small planet next to a bright, close, binary pair of stars. But it is worth remembering that gravitational instability of exactly the kind described here is also a live possibility for why any planets that formed there long ago might simply no longer be in a findable, stable orbit at all. Across the full confirmed exoplanet catalog, roughly 1 in every 10 known planets orbits a star that has at least one stellar companion somewhere in the system, whether a close binary partner or a much wider, more distant one. That fraction is almost certainly an undercount of the true rate, since a faint, wide companion star is considerably harder to detect than the planet itself in many surveys. Meaning, a meaningful number of apparently single-host stars cataloged today likely have a companion nobody has confirmed yet. Every one of those systems, known or not yet known, carries the same underlying sorting mechanism at work in the background, quietly favoring planets tucked in close or thrown out wide, and quietly working against anything caught in between. Our own sun, worth remembering, is itself something of an outlier in this respect. Most stars of similar mass to the Sun do have at least one stellar companion, which makes a single, solitary star like ours somewhat less typical than casual intuition might suggest. Whether that solitary status played any meaningful role in how calmly and stably Earth's own orbit was able to settle down billions of years ago is difficult to prove directly, since we only have the one solar system to examine closely. But given everything covered in this section, the absence of a second or third star tugging at Earth's orbit from an unstable middle distance is, at minimum, one more item on the list of conditions that happen to go Earth's way rather than against it. Think about how a city actually sounds at night, if you happen to live somewhere with constant, quiet construction and demolition going on across town. The kind of ordinary urban background noise nobody really notices anymore. You do not hear the whole city being built and unbuilt at once. You hear a truck reversing somewhere a few streets over. You hear a distant, muffled crash that could be anything, gone again before you can place it. Once, in a great while, if you happen to be standing at exactly the right corner at exactly the right moment, you watch an entire building come down in real time, and for a few seconds you get to see, directly, the kind of event that is normally only ever inferred from noise and rumor and the empty lot that shows up afterward. Everything covered tonight has been exactly that kind of glimpse. A distant crash, caught on an old recording, 12,000 light-years away. A building visibly leaning, mid-collapse, close enough to watch continuously for years. Ash and rubble found sitting quietly on far more properties than anyone expected when the inspectors finally thought to check. None of it is the whole picture. All of it, taken together, tells you the demolition work is not rare. It is one of the ordinary sounds of the neighborhood, running constantly, mostly out of sight, whether or not anyone happens to be standing on the right corner to notice. Not every mechanism covered tonight destroys a world completely, and it is worth being fair about that distinction before closing. A stripped atmosphere leaves behind a smaller, harder planet rather than nothing at all. A star swallowing a hot Jupiter still leaves the star itself intact, slightly larger, slightly changed. An ejected rogue planet is not destroyed in the sense of being torn apart. It is simply cut loose, still whole, still a planet, just permanently alone. Only a handful of these fates, the shredding into a white dwarf's debris disk, the vaporizing collision between two young planetary bodies, actually end with the world's material being broken down and reabsorbed into something else entirely. The rest are transformations rather than annihilations. Planets continuing to exist in some altered, diminished, or exiled form rather than ceasing to exist altogether. That distinction matters, because it means the true count of worlds no longer capable of supporting anything resembling the version of Earth we know is considerably larger than the count of worlds that have been erased. Outright. Diminishment, on these numbers, appears to be far more common than obliteration. Add it all up, and a shape starts to form that is very different from the two pictures most people carry around in their head when they think about the universe. It is not simply crowded with company we have not met yet. It is not simply empty and silent either. What the actual evidence points toward is something closer to a very large, very old demolition site, mostly hidden from view, where we only ever catch small, scattered pieces of the work in progress. There is also a slower, less dramatic category worth naming, honestly, because not every dead world makes for a striking headline. Some planets simply drift out of the range where anyone would think to look for them at all, orbiting a star that is faded, or sitting at a distance so wide and so cold that no survey currently running is tuned to notice them. These are not destroyed in any of the specific senses covered tonight. They are simply overlooked, sitting quietly outside the boundaries of what our current instruments are built to search, waiting for a future generation of telescopes or a future generation of astronomers with a different set of questions to finally take an interest in that particular patch of otherwise unremarkable sky. It is worth remembering that the census described tonight, thorough as it has become, is still bounded by the limits of what current instruments can actually detect, and there is almost certainly a further population of quietly overlooked worlds sitting just outside the edge of what any of tonight's evidence could have found in the first place. Say it plainly first, in short pieces, before assembling the whole shape. Planets get thrown out of their own systems. Planets get swallowed by their own star. Planets spiral inward on a clock we can already measure. Planets get shredded into dust that settles onto the corpse of a dead star. Planets collide with each other while they are still forming. Planets lose their entire atmosphere to their own star's radiation. Planets sitting in the wrong neighborhood of the galaxy get irradiated by an explosion they never saw coming. None of these are competing theories, arguing over which single explanation is the real one. They are simply different, independently confirmed ways the same basic outcome keeps happening over and over, all across the galaxy. At the same time, we have watched a planet get swallowed whole in real time, in a star system 12,000 light-years away, an event so rare that it took 3 years just to convince ourselves of what we were looking at. We know of at least one planet, much closer to home, orbiting only about 1,000 light-years away, currently mid-collapse on a measured, shrinking clock of roughly 3 million years. We know that somewhere between 1/4 and 1/2 of all white dwarfs studied are actively receiving debris from shredded rocky worlds, meaning the destruction of planetary systems around aging stars is not a rare curiosity. It may be closer to a routine, ongoing background process happening across the galaxy right now. We know that a meaningful slice of all planets ever formed close to their star simply had their atmosphere boiled away entirely. Some slowly over hundreds of millions of years, some fast enough to watch changing month to month. We know that a planet's own galactic address, whether it sits in a quiet outer arm or a crowded, radiation-heavy core region, shapes its odds of survival before its chemistry or its orbit ever get a chance to matter. And we know that roughly half of all stars come in pairs or triples, systems that reliably eject a share of their own planets into permanent, starless darkness as a simple, predictable consequence of orbital mechanics, feeding directly into a rogue planet population that may already outnumber every star in the Milky Way combined. Set this against the raw scale of what is actually out there. More than 6,000 planets beyond our own solar system have now been confirmed, catalogued one by one from the telltale dimming of a star or the small gravitational wobble a planet induces in its host. And that number keeps climbing every month as new surveys come online. Set beside an estimated few hundred billion stars in the Milky Way alone, most of which appear to carry at least one planet, The confirmed catalog is still a tiny fraction of what almost certainly exists. Every single mechanism covered tonight, the ejections, the engulfments, the shredding, the collisions, the boiling away, the wrong address inside a dangerous galaxy, has already been confirmed acting on individual, named members of that small confirmed catalog. Scale any of those confirmed rates up across the full, largely unconfirmed population still waiting to be found. And the raw number of worlds that have already been destroyed. In every sense this conversation has described likely dwarfs the number currently intact by a margin too large to comfortably picture. None of these mechanisms were things astronomers could describe with this much specific, direct evidence even 20 years ago. Rogue planets were speculation. Planetary engulfment was theory, built from indirect chemical clues. Orbital decay in a hot Jupiter was a hypothesis waiting for one lucky, patient decade of timing data. White dwarf pollution was an odd spectral curiosity before anyone connected it convincingly to shredded worlds. All of it has become concrete, direct, observed evidence only within roughly the last 15 years, which is itself worth sitting with for a moment. We are the first generation of humans who get to see any of this happening, rather than simply reason our way towards suspecting it. It is worth asking, briefly, what changed to make all of this possible within a single human lifetime, since the physics itself did not change at all. 3 separate developments arrived at roughly the same time and reinforced each other. Space-based telescopes, freed from the blurring effect of Earth's own atmosphere, made it possible to measure tiny changes in brightness and position with a precision no ground-based instrument could match. Digital detectors replaced photographic plates, turning astronomy into a discipline that could record, store, and statistically compare enormous quantities of data rather than relying on a human eye squinting at a single photographic exposure. And decades-long survey projects, built specifically to stare at the same patches of sky over and over, rather than moving on after a single observing night, finally accumulated enough repeated measurements of the same stars to notice slow, subtle changes unfolding across years rather than minutes. None of these 3 developments was really about astronomy specifically. They were about patience, storage, and computation, becoming cheap and reliable enough to apply at a scale nobody could have managed by hand a single generation earlier. The evidence for a universe full of dead and dying worlds was always there, in the light arriving every night. What was missing, until quite recently, was simply the capacity to notice it. Here is the part that is easy to miss if you move too quickly through all of this. Every single mechanism described tonight, the swallowing, the shredding, the boiling away, the ejection into darkness, the wrong address inside a dangerous galaxy, requires a planet to have existed first. None of this is a story about a universe that failed to make planets. It is the opposite. It is a universe that appears to make planets constantly, in enormous numbers, around nearly every star it forms, and then puts almost all of them through some version of a filter that a meaningful share of them simply do not survive intact. The silence people usually point to when they wonder whether we are alone might not be evidence of an empty universe at all. It might be evidence of a universe that is unusually good at building worlds, and only occasionally lets one of them keep running long enough for anything on it to notice what is happening. Which brings the conversation, as it eventually has to, back to the planet you are actually standing on. Earth has, so far, avoided every single mechanism covered tonight. No wandering star has ever pulled it loose from the sun's gravity and cast it into permanent darkness. The way happens to a meaningful share of planets in binary systems. The sun has never expanded far enough, yet, to reach down and swallow it the way a much older star did to its own planet in Aquila. Earth's atmosphere has never been stripped away by youthful stellar radiation because the Sun, even in its early history, was never quite energetic enough in the right wavelengths at the right distance to finish that job the way it did to countless closer, smaller worlds elsewhere. No supernova has gone off close enough. In 4.5 billion years of orbiting a quiet stretch of a spiral arm to strip away the ozone layer and end the whole experiment early. Every single filter this conversation has walked through, Earth has, so far, quietly passed through without ever noticing. Consider, for a moment, how many separate rolls of the dice that actually represents. Earth's orbit had to avoid the kind of chaotic, destabilizing gravitational tug-of-war that ejects planets from binary systems. And it did, because our Sun formed alone rather than with a close stellar partner. Earth had to avoid sitting close enough to the Sun for tidal forces to ever begin meaningfully dragging its orbit inward, and it did, because it settled at a comfortable distance early in the solar system's history and has stayed there ever since. Earth had to hold on to enough atmosphere against the Sun's youthful radiation to keep liquid water on its surface. And it did, helped considerably by its own size, its own gravity, and a magnetic field strong enough to deflect the worst of what the young Sun was putting out. Earth had to avoid a sufficiently close supernova for over 4 billion consecutive years running, in a galaxy where such explosions happen roughly every few decades somewhere within its disk. And it did, purely as a matter of location rather than any active defense the planet mounted on its own behalf. None of these were guaranteed outcomes. Each one was a separate condition that had to hold independently for the entire span of the planet's existence so far, and each one still has to keep holding for exactly as long as anything on this planet wants to keep going. That does not mean any of these mechanisms are finished with the solar system. The Sun, billions of years from now, will eventually swell the same way ZTF's star did, and there is serious scientific debate over whether Earth's own orbit will be far enough out by then to escape being swallowed the way that far-off planet in Aquila was not. But that ending, if it comes at all, is still billions of years away, further in the future than complex life has even existed in the past. Right now, today, this planet is one of the rare entries in this entire survey that still gets marked as intact rather than destroyed, stripped, shredded, or cast loose. There is something worth carrying with you the next time you happen to look up on a clear night. Most of what astronomers now understand about dead worlds did not come from finding empty, silent skies and concluding that nothing is out there. It came from finding specific, individual pieces of wreckage, a flare in an old archive, a shrinking orbit around a distant hot Jupiter, a scattering of heavy metal contamination in a white dwarf spectrum, a nebula full of drifting starless pairs, and piecing together, one confirmed case at a time, just how much destruction the ordinary life of a galaxy actually produces. The universe is not quiet because it is empty. It may be quiet because so much of what it built has already come and gone, ground down slowly or ended suddenly, long before we ever pointed an instrument in that direction. None of this is a reason to feel small in the discouraging sense of the word. If anything, it works the other way. A universe this thorough, about tearing worlds apart through so many separate and unrelated mechanisms, gravitational, thermal, radiative, chemical, is not a universe that is simply indifferent to planets in some vague, abstract way. It is a universe actively, constantly working against the specific, narrow set of conditions any planet needs to hold on to in order to keep functioning as a stable home for anything at all. Every rocky world that has managed to avoid every single one of these fates for 4.5 billion years running has, in a very real sense, been threading a needle the entire time, whether or not it had anyone on it aware enough to notice the needle was even there. Earth is still here. That is not a small thing, and it was never guaranteed. It is one surviving case, sitting in the middle of a very large, very old count of worlds that did not make it this far. Still turning, still holding its air, still far enough from anything that could have already ended it. Whatever is happening in your life tonight, whatever brought you to sit still and listen to something like this for the better part of an hour, is happening on the one planet in this entire survey that gets to keep going. The next clear night you get, find a single star and hold your eyes on it for a little longer than you normally would. You will not be able to tell, just by looking, whether that star still has a full, intact family of planets circling it quietly, or whether one of them is already spiraling inward on borrowed time, or whether what used to orbit it has already been ground into dust and fed back into the star itself. The light looks the same either way. That is, in the end, the real shape of this entire conversation. Not a galaxy quietly waiting to be discovered, and not a galaxy sitting empty and finished. A galaxy still working, constantly, mostly unseen, building and unbuilding worlds on timelines too long for any one lifetime to witness in full, of which we have only just begun to catch the occasional glimpse. If tonight has changed even slightly how you look at the sky, go ahead and like the video and subscribe for more of these journeys into the cosmos, because there is a great deal more of this universe still worth sitting with together. Now, wherever you are listening to this, let the night be quiet for a moment, and let that be enough.